Hi guys, today I would like to discuss about applications of Gauss law. So we practiced certain cases how to find electric field due to because of multiple charge distributions. But suppose if you have some symmetric charge distributions or charge configuration. What does it mean symmetric charge configurations? So here we are having in this session we are having 3 to 4 examples, means charge is uniformly distributed throughout the surface. Suppose in this picture you can see the charge is uniformly distributed throughout its length. So otherwise if you take a sphere, so over the sphere a charge is uniformly distributed. So if you have certain cases of like that, so those we mention as symmetric charge configurations. So if it is symmetric charge configurations, to find electric field at a given point is very handy. It means it's very easy by using Gauss's law. So to apply Gauss's law, we need to have symmetric charge distribution. Why the charge distribution should be symmetric? Because Gauss law is having like this integral E bar dot ds bar equal to q by epsilon naught, charge enclosed by epsilon naught. So our condition is that the charge distribution is symmetric. If charge distribution is symmetric, what is the advantage? The advantage is that the electric field is a constant. So here the electric field remains constant. How we recognize that? Suppose if you have a long positively charged object, so you know since it is a positively charged object, the electric field lines are coming out. Suppose if you watch this charged object from the top view, just like this, you can see the all electric field lines are coming out symmetrically, equally. So if that is the case, we can argue that the electric field at here is constant. If this term is constant, what is the advantage? So we need not to do any integration. It will be pulled out of the integration and we need to do only surface integration, the Gaussian surface integration. If charge distribution is symmetric, the main advantage in the Gauss's law is the electric field becomes constant. If electric field becomes constant, need not to worry to do the integration. Means our problem will become half. Just we need to do only integration for this Gaussian surface what we have chosen. And the rest of the parts we can be do it. So like that we can find out electric field due to this symmetrical charge distribution at a given point. So these we will discuss under the applications of Gauss's law, and this Gauss's law we only apply mainly, not only, we mainly apply to symmetric charge distributions. Again I am stressing what is the advantage of this symmetric charge distribution. If charge distribution is symmetric, in the Gauss's law, the electric field term becomes constant. So let us see one by one. So I would like to discuss the first one. Suppose if I have an object that is infinitely long, straight, uniformly charged wire. So this is my object. The object is given at here, an infinitely long, straight, uniformly charged wire. So because of this object, I wish I would like to find electric field at a given point. Let us do that. So let's write what is given. So if I can write what is given, so given to me infinitely long charged object having linear charge density lambda. And what to do? What is my task? What shall I do? So I need to find the electric field at a distance r bar by using Gauss theorem. So let me make a figure for that. Suppose if we take this is infinitely thin object, so it is charged object. I wish I would like to put charges on this object. So this is my infinitely long charged object with a charge density. Now I wish I would like to find an electric field at a given point r. So here I need to assumption my Gaussian surface. So there is always a link between the symmetrical object and Gaussian surface. So Gaussian surface is just like a clever selection of certain surface which makes us too easy to find out. So we need to do such a clever selection. Based on that clever selection of the surface, we need to select it. So always there is a matching between the Gaussian surface and the charged object. If we take that type of Gaussian surface, then our work will become very easy. So here my useful Gaussian surface to this. My useful Gaussian surface at here is a closed cylinder. So it means, suppose on this infinitely charged object, suppose if I draw a cylinder, it should be perfect in shape. So this is my Gaussian surface. Now I wish I would like to find electric field at a given point. So at this point, so this is at a distance r from the charge distribution. I would like to find what is the electric field due to because infinitely long charged object. Now when you select a Gaussian surface, here you remember always we need to look after how the electric field is interacting with the surface. Electric field and ds. So that is the main key point in the Gauss theorem. We need to look after always how the electric field is interacting with the Gaussian surface. Suppose if I draw a perfect diagram for that, suppose if I take a picture of this one, which is already given in the handout. So to this infinitely long object, so this is the Gaussian surface here we have taken. Now here you can see this cylindrical surface having three surfaces, means the upside face and the downside face and the cross sectionals. So the S1 you can take as a curved surface area, and the S2 you can take as an upside cylindrical surface, and S3 you take as a downside cylindrical surface. Now from the positive charge, we know that how the electric field lines move. The electric field lines move from the positive charge radially outwards. So from the S1, the electric field lines move along in this direction. From the S2 also, since it is a positively charged, the electric field move along in this direction. From the S3, the electric field lines will also move along in this direction. So these are the electric field directions, radially outward. Now Gauss law gives the relation between electric field and the surface area of the Gaussian surface. Now, yet here you can see the ds1 is the area vector of this curved surface area, and here the ds2, this is the area vector of this surface s2, and the ds3 is the area vector of the surface s3. Suppose if I draw area vector at here on each surface, on this curved surface area, the area vector is along the field direction vector. But if you can draw at here, since this is the surface which I like to shade, so this is the surface S2. Now what is the area vector on the S2? Area vector is on S2 is showing upward direction. So this is the area vector ds2. And similarly, if you can take the surface S3 which is in the down part, so this is the surface S3. And what is the area vector? The area vector is showing now in this downward direction. So I can draw the area vector from it here. So this is the area vector which is showing in the downward direction. And a part of these two, which is the leftover area, so the leftover area is the curved surface area. So if I wish, I would like to highlight the curved surface area S1. So this is the curved surface area from the Gaussian surface. Okay. Now we will jump on to the derivation. Now what the Gauss law says? The Gauss law says the flux, the total flux, electric flux equal to closed integral of area E bar dot ds, which equal to q by epsilon naught, charge enclosed. But here you can see the total area E bar dot ds is nothing but the electric field times surface S1, so that I can write as a ds1 plus the closed integral of E bar dot ds2 plus closed integral of E bar dot ds3. Since here we are having three surfaces. Now, what is the value of closed integral of E bar dot ds1, which equal to, it is the dot product of two vector. I can write closed integral of E ds cos E ds1 cos theta. And what is the angle between them? The angle between the electric field vector and area vector goes to 0. It means theta equal to 0 degree at here. You will get the value closed integral of E ds1. Same value you can get it. But what about the surface S2? Suppose if I can find what is the closed integral of E bar dot ds2, is equal to closed integral of E bar ds2 cos theta. What is the theta at here? If you can see, the area vector and electric field vector. So the area vector and electric field vector, they both are the perpendicular. So here theta equal to 90 degree. So cos 90 value will becomes 0. So the entire term will become 0. Therefore E bar dot ds2, this contributes 0 electric field. Similarly, you can see the closed integral of E bar dot ds3, the third surface. So this is also you can write. So which is equal to closed integral of E bar or ds3 cos theta. From the third surface also, if you observe theta equal to 90 degrees, it means the electric field vector and the area vector, they both are the perpendicular. So cos 90 value becomes 0. So we can get this value 0. So the electric field and the third surface will be contributes as 0. Now to get the total electric field, so in this expressions, if I wish, I can substitute the total electric field. The total electric field, so the closed integral of E bar dot ds bar equal to closed integral of E bar dot ds1 plus 0 plus 0, because other two surfaces they contributed 0. So now the total electric field E bar dot ds is only contributing the flux due to the curved surface E bar dot ds. According to Gauss's law, according to Gauss's law, according to Gauss's law, the closed integral of E bar dot ds, which equal to charge enclosed by epsilon naught. So from the above expressions, I got the total electric field is just only the curved surface area. So in the place of, I can substitute this value. So I can get, so closed integral of E bar dot ds1. So here I left over only the curved surface area only, which equal to Q upon epsilon naught. Under the Q, it's the charge enclosed. Now I can pull E bar outside integration because electric field is symmetry. We need not do any integration. E bar closed integral ds1 equal to charge enclosed upon epsilon naught. Now if you can take the formula of a curved surface area, that is equal to 2 pi r L. So here L equal to the length of the cylindrical surface. So here the L equal to length of the cylindrical surface and the area of this curved surface. So the area of the curved surface which equal to 2 pi r L, which equal to charge enclosed upon epsilon naught. So that is the closed integral ds1 value here equal to 2 pi r L. So that is the surface area of a curved surface. Now we are at the end, but here you can see the given is infinitely long charged object. So if it is infinitely long charged object, we need to talk about what is the charge contains. So if you remember linear charge density, that is nothing but lambda. Lambda we are calling linear charge density, which equal to, according to formula, lambda equal to charge per unit length. So for this infinitely charged object, we will use this one as linear charge density, charge per unit length. Now I will write what is the charge at here. Q is equal to lambda times L. It means the total charge in this infinite line, infinite wire, is equal to lambda times L. Or in the question itself, they already mentioned that it's having linear charge density lambda. So according to linear charge density definition, the linear charge density lambda equal to Q by L. So here the Q equal to lambda times L. Now you can substitute the Q value at here. It becomes E bar times 2 pi R L equal to lambda times L upon by epsilon naught. So now you can cut L on both sides. Now the leftover term is, we need to find electric field. E bar equal to lambda by 2 pi epsilon naught R. So the electric field at a distance R, the expression for the electric field at a distance R, due to this infinitely long charged object. So this is the final expression. The electric field at a given point, at a distance R from a uniformly charged infinitely charged, that you mentioned, infinitely charged object. So the final expressions we can mention that E bar equal to, so E bar equal to lambda by 2 pi epsilon naught R. So here lambda is nothing but linear charge density and 2 pi epsilon naught constant terms, and R is the distance. So in this case, electric field is inversely proportional to 1 by R. So this is the final expression. The electric field due to an infinitely charged object